Hello, and welcome to Sleep with Science. I'm so glad you've joined tonight's quiet journey. Let the day slowly dissolve behind you. Feel your breathing settle in and out, each breath taking you a little farther from your worries and a little closer to the stars. Tonight, we'll drift through one of the most fascinating puzzles ever imagined. Can the universe be infinite and still have an edge? It's a question that mixes wonder with paradox. Infinity feels boundless, yet edge suggests a border, a final frontier where something ends. How could both ideas live inside the same universe? As you relax, we'll move gently through 5 cosmic chapters. 1. What infinity means in the language of science. 2. Why the universe appears to expand and what that says about its shape. 3. The strange possibility of other universes beyond our own. 4. The hidden geometry of space itself. 5. And, finally, the future, how everything we know might fade, stretch, or fold into silence. No need to stay awake for every word. Even as you drift, your mind can wander freely among galaxies. Let's begin. Close your eyes, if they aren't closed already. Picture the night sky, not as tiny lights, but as windows into billions of suns. Every point of light is another world, and between those lights stretches darkness, vast, deep, and quiet. For centuries, people have asked, how far does it go? The ancient Greeks imagined a crystalline sphere holding the stars. Beyond it lay nothing, pure void, unreachable. Later, philosophers like Giordano Bruno dared to suggest the stars were other suns, each surrounded by worlds, perhaps with beings of their own. For this radical thought, he was condemned, but his vision was closer to what we now know. Then came Isaac Newton, who saw space as endless and absolute. In his universe, every star's gravity pulled on every other, forever, an infinite web of attraction. But infinity troubled even Newton. If space were truly endless and filled with stars, then the night sky should shine with the light of countless suns, so bright that darkness itself could not exist. Yet, we see blackness between the stars. This puzzle, later called Olber's paradox, whispered that something was missing. Centuries later, Einstein arrived with relativity, and with it, a new way to think about space, not as a stage where events happen, but as something dynamic, curved, alive. Gravity, he said, isn't a pull across empty space. It is the bending of space itself. Planets don't feel a force, they simply follow the curves. Einstein first imagined a static, finite universe, a cosmic bubble where space curved back on itself, like the surface of a sphere. Travel far enough in one direction, and you'd return to where you began, never finding an edge, because there is none, to keep it from collapsing under its own gravity. He added a mathematical tweak, the cosmological constant. Later he called that tweak his greatest mistake, yet it may turn out not to be a mistake at all. In 1929, Edwin Hubble peered through his telescope and saw galaxies rushing away from us. The farther they were, the faster they fled. Space itself was stretching, expanding. That discovery changed everything. The universe wasn't static, it was evolving. If it's expanding now, it must once have been smaller, denser, hotter. A single radiant moment we now call the Big Bang. So, the universe has no center like an explosion in empty air. Everywhere expands away from everywhere else. Imagine dots on a balloon's surface. As the balloon inflates, each dot sees the others receding. That's our universe, except the balloon's surface isn't two-dimensional. It's the three-dimensional fabric of space itself. And now the word infinite enters again. If expansion began from something tiny, does that mean it started finite and is now infinite? Or was it infinite from the start, each region expanding away from its neighbors forever? Cosmologists still debate this. Infinity in physics is slippery, more a concept than a measurement. We can observe only a limited region, a bubble about 93 billion light-years across. Because light from beyond that horizon hasn't had time to reach us. That's the observable universe, the part we can see. Beyond it might stretch space without end. Or it might wrap back on itself in ways our senses can't perceive. The notion that infinity can exist without an edge is easier to imagine with analogies. Think again of that balloon. The surface is finite but has no edge. A tiny creature crawling across it would never find a border. Yet the surface is not infinite. It just loops back. Now imagine inflating the balloon endlessly. The curvature becomes so gentle that, locally, it feels flat. That could be our universe, so vast and slightly curved. That to us it appears infinite and edgeless at the same time. As you listen, feel how immense that is. You are a collection of atoms forged in ancient stars, floating in a galaxy among billions, in a universe that may have no boundary at all. And yet, right now, you can sense its depth from your quiet room. Through sound, through thought, through wonder. In our next gentle segment, we'll explore what scientists mean when they speak of the edge of the universe. Is there really a border where space stops? Or is the edge something different? A horizon? A limit not of space itself, but of what we can know? The idea of an edge of the universe has fascinated thinkers for millennia. When we imagine an edge, we think of a border, a place where something ends and something else begins. But what could possibly lie beyond everything? For ancient civilizations, the cosmos often had literal boundaries. To the Babylonians, the sky was a solid dome arching over a flat earth. The Egyptians imagined a heavenly river carrying the sun across the sky each day. Even the early Greeks thought the stars were embedded in a crystalline shell. In all of these visions, there was an edge, a final outer wall containing all that existed. But as science evolved, that simple picture dissolved. The telescope shattered the notion of a fixed sky. Galileo's observations showed that the heavens were not perfect spheres but dynamic, endless expanses of stars and planets. Later, the work of Hubble and Einstein painted a universe that had no physical edge, but still had a limit not of space, but of observation. This is where the concept of the cosmic horizon appears. Because light travels at a finite speed, and the universe has existed for only about 13.8 billion years, there's only so far we can see. That distance, about 46 billion light-years in every direction, defines the observable universe. It's not an edge in the traditional sense. It's more like a horizon at sea. From your position on the ocean, you can only see as far as the curvature of the Earth allows. Sail beyond that point, and new scenery appears, but the planet doesn't end. Your view simply shifts. In the same way, the universe may continue far beyond our cosmic horizon, but the light from those distant regions hasn't had time to reach us. It's not that space stops there. It's just that, beyond that boundary, information hasn't arrived yet. Every year, as the universe ages, that horizon expands, allowing us to see a little more of the cosmos, but only within the limits set by the speed of light and the expansion of space. This expansion adds another twist. Because space itself is stretching, some galaxies are receding from us faster than light, not because they're moving through space that fast, but because the space between us and them is growing. Their light will never reach us. Those galaxies lie beyond a future horizon, forever disconnected from our observable reality. So, when we ask whether the universe has an edge, the scientific answer is both simple and profound. No, space itself has no physical border. But yes, there is a limit to what we can observe. The true edge of the universe is not a wall in space, but a wall in time and information. Imagine standing on the shore of a vast ocean at night. You can only see the water illuminated by the starlight above. Beyond that faint glow lies darkness, not because the ocean ends, but because the light cannot reach that far. That is our cosmic situation. We are standing on the shore of visibility, looking out into an infinite dark sea. Scientists describe this boundary as the surface of last scattering. It's the farthest distance from which light, specifically, the cosmic microwave background radiation, can reach us. This radiation was released about 380,000 years after the Big Bang. when the first atoms formed and the universe became transparent. Before that moment, space was a dense fog of charged particles. Light couldn't travel freely, so anything before that time is hidden from direct observation. We can infer what happened, but we can't see it. That's the earliest visible edge of our universe. The concept challenges intuition. In our daily lives, edges are physical, the edge of a table, the end of a road. But in cosmology, an edge can be conceptual, defined by what can or cannot be observed, not by where things stop existing. Some cosmologists compare our universe to a video game world. Within the game, characters can walk endlessly, exploring new landscapes. But from outside, we know the world is limited by code and geometry. The characters can never reach the end. They exist entirely within the rules of their simulated space. If our universe is something like that, a finite yet unbounded structure, then asking what lies outside may not even make sense. Space and time themselves could be self-contained. There may be no outside to step into. This idea leads naturally to a deeper question. If space has no physical edge, could there be other universes, separate realms where space and time start anew? And if so, what would that mean for our own cosmic story? The more scientists have studied the universe, the more a strange question has emerged. What if our universe is not the only one? For centuries, the word universe meant everything that exists. But in the past few decades, physicists have started to wonder whether everything might actually be just one small part of a much greater cosmic structure, a multiverse. At first, the idea sounds like pure science fiction. Countless universes, each with different laws of physics, existing side by side like bubbles in an unseen sea. But surprisingly, several branches of modern science point toward this possibility, not as fantasy, but as a logical outcome of what we already know. The story begins with the Big Bang. When the universe first emerged, it wasn't a quiet expansion. It was an explosion of unimaginable energy, followed by a brief but extraordinary event called cosmic inflation. In the first fraction of a second, less than a trillionth of a second, the universe expanded faster than the speed of light. Inflation helps explain many mysteries. Why the universe looks so smooth, why it's nearly the same temperature everywhere, and why space seems flat on the larger scales. But inflation also opened a door to something much larger. In most versions of the theory, inflation doesn't stop everywhere at once. It slows down in some regions, like ours, forming bubble universes, while in other regions, it continues endlessly. Each bubble becomes its own separate universe, with its own space, its own time, and possibly its own physical laws. Together, these bubbles make up the multiverse, a vast foam of universes growing within an infinite cosmic field. Our universe, then, might be just one bubble among countless others. Each bubble could have different constants of nature, one where gravity is stronger, another where atoms can't form, and maybe even some where life, stars, and galaxies could never exist. It's a breathtaking idea, one that transforms the Big Bang from a single event into a never-ending process, a cosmic generator creating new universes forever. The theory of eternal inflation, developed by physicists like Alan Guth and Andre Linde, suggests that inflation is not a one-time event. Instead, it's a self-replicating process. Quantum fluctuations, tiny random variations in energy, cause inflation to end in some regions while continuing in others. Those regions that stop inflating become isolated universes, disconnected from the rest. Imagine an endless field of energy, like a vast ocean. In that ocean, small bubbles form and drift apart. Each bubble is a universe. The ocean around them is the inflationary field. Inside each bubble, time flows, stars are born, and galaxies evolve. But between the bubbles, space itself is still inflating faster than light, pushing them apart forever. This means that, from a cosmic point of view, the creation of universes never stops. Even as our own universe ages, new universes may be forming elsewhere in the multiverse. Some may have already collapsed. Some may just be beginning. Others may last for trillions of years longer than ours. But eternal inflation is only one path to the multiverse. Quantum mechanics, the science of the very small, offers another. In the quantum world, particles can exist in many possible states at once, a phenomenon called superposition. When we observe them, that superposition appears to collapse into one outcome. But some interpretations, like the many worlds interpretation, suggest that all outcomes actually happen, each in its own branch of reality. In this view, the universe splits continuously, creating new versions of itself for every quantum event. Every choice, every coin flip, every interaction of particles, all of them branch into separate, parallel universes. You, in one world, turned left. In another, you turned right. In one, Earth formed as it did. In another, small differences changed the entire course of history. If this theory is true, the number of universes is unimaginably vast, perhaps infinite, each one containing a slightly different version of reality. And just like the bubbles of eternal inflation, these quantum universes would be independent, inaccessible, and complete. It's a strange picture, an infinity of infinities, branching endlessly. But mathematics and physics don't rule it out. In fact, some equations of quantum theory naturally produce this outcome if taken literally. A third path to the multiverse comes from string theory, a framework that tries to unite all of physics, gravity, quantum mechanics, and the fundamental forces into one theory. According to string theory, the smallest building blocks of nature aren't particles, but tiny vibrating strings of energy. The vibrations of these strings determine the properties of particles, their mass, charge, and behavior. However, for the mathematics to work, string theory requires extra dimensions, not just the 3 of space and 1 of time we experience, but as many as 10 or 11 total dimensions. Most of these dimensions are thought to be compactified, curled up at incredibly small scales, beyond our ability to detect. What's fascinating is that there are enormous numbers of ways these extra dimensions could be shaped. Each possible configuration produces a different version of physical laws, different particles, forces, and constants. Physicists call this collection of possibilities the string landscape, and it may contain as many as 10 to the power of 500 different universes. That's a number so large it defies comprehension, more than the number of atoms in the observable universe. If the multiverse is real, our universe could simply be one valley in this immense landscape, one stable configuration among trillions of others. Most of the other universes might be sterile, empty, or unstable. But a few, like ours, might have the right balance for galaxies, stars, and life to form. This brings us to a deep and controversial idea, the anthropic principle. It asks a simple question: why does the universe seem perfectly tuned for life? The forces of nature are balanced with extraordinary precision. If gravity were slightly stronger, stars would burn out too quickly. If it were weaker, they might never ignite. If the charge of the electron were a little different, atoms couldn't form stable structures. Every constant seems fine-tuned to allow complexity and consciousness to exist. One possible explanation is coincidence, that we just happen to live in a universe that works this way. But the multiverse offers another. If countless universes exist, each with different physical constants, then it's not surprising that we find ourselves in one where life is possible. We could only exist in a universe compatible with our existence. In all the others, there may be nothing at all to ask the question. To many scientists, this line of thinking feels unsatisfying. It shifts the mystery rather than solving it. But it also fits neatly with what we observe. The universe doesn't seem designed for us. It's just one version among an infinite ensemble where the right conditions happen to occur. Of course, the great challenge of the multiverse is evidence. By definition, if other universes are beyond our cosmic horizon, we can't observe them directly. So how could we ever prove they exist? Physicists have proposed a few intriguing possibilities. One involves looking for subtle imprints left over from collisions between bubble universes in the early inflationary era. If another universe brushed against ours billions of years ago, it might have left a circular scar, a faint pattern, in the cosmic microwave background radiation. Another approach is indirect reasoning. If certain features of our universe, like the value of dark energy or the masses of elementary particles, seem statistically rare or fine-tuned, that could hint that we are part of a larger ensemble where different values occur elsewhere. For now, these remain speculative, but science has often turned imagination into discovery. Once, galaxies were invisible to us. Once, atoms were a theory. So perhaps, in some far future, the multiverse too will move from possibility to evidence. If the multiverse is real, it reshapes everything we think about existence. It means that our universe may not be the central stage of creation, but just one scene among countless others. It challenges the uniqueness of everything, even ourselves. It suggests that what we call reality is only one version of an endless story, repeated and rewritten across infinite canvases of space and time. It also raises profound questions. If other universes exist, can they ever interact? Could a black hole in our universe be a doorway to another? Some theories propose that each black hole might spawn a new universe inside, connected through the mathematics of spacetime. In this view, the multiverse isn't just a static collection. It's an evolving family tree, with each universe giving birth to others through gravitational collapse. Others suggest that quantum entanglement, the mysterious link between particles, could, in some deeper way, connect distant universes. Perhaps, on a level we don't yet understand, all universes are part of a single, unified structure, many worlds woven into one cosmic fabric. No one knows for certain. But what's clear is that our understanding of everything keeps expanding. Each time we draw a boundary around the universe, new evidence pushes it outward. What once seemed infinite becomes just a small part of a grander whole. As extraordinary as the multiverse sounds, it also reminds us of something humbling. Even if infinite universes exist, we still experience just one. This one, the universe that allowed life to arise on a small planet orbiting a yellow star. A universe where atoms forged in dying stars combine to create beings capable of asking these questions. Whether or not other universes exist, this one remains precious. Every star we see, every galaxy in the night sky, every molecule in our bodies, they all belong to this particular branch of reality. We are the consciousness of this cosmos, the way it has found to look at itself. And perhaps, even if there are infinite versions of us scattered across the multiverse, it doesn't make this one any less meaningful. It only deepens the mystery and the wonder of being here at all. Since the dawn of human curiosity, we have looked up at the sky and asked the same timeless question: what is the shape of everything? When you stare into the stars on a clear night, the universe seems infinite, an endless sea of darkness scattered with light. But is it truly infinite? Or does it curve back on itself like the surface of a sphere, where traveling far enough in one direction could eventually bring you back to where you started? For thousands of years, this question has haunted philosophers, scientists, and dreamers alike. And today, thanks to the combined work of cosmologists, mathematicians, and space telescopes, we are closer than ever to understanding the true geometry of the universe. To grasp the shape of the universe, we must first understand what that even means. When we speak of the universe's shape, we are not talking about the shape of galaxies, planets, or clusters of stars. We are talking about the shape of space itself, the invisible fabric that holds everything. Einstein's theory of general relativity changed our understanding of space forever. Before Einstein, space and time were thought to be rigid, an empty stage where events played out. But Einstein showed that space and time are flexible, dynamic, and woven together into a single entity called spacetime. Matter and energy tells spacetime how to curve, and that curvature tells matter how to move. Planets orbit stars not because they are being pulled by a mysterious invisible force, but because the space around the star is curved, guiding the planet's motion like a marble rolling in a bowl. This curvature doesn't just happen around stars and planets. It can exist on cosmic scales. If there's enough matter and energy in the universe, it can cause the entire universe to curve in one of several possible ways. 3 possibilities: closed, flat, or open. Cosmologists describe 3 fundamental types of spatial curvature for the universe. A closed universe, shaped like a sphere. In this model, space curves back on itself. You could, in theory, travel far enough in one direction and end up where you began. much like walking around the surface of the Earth. A closed universe has positive curvature and a finite volume. It has no edges, but it is not infinite either. A flat universe, shaped like an infinite sheet. Here, space has zero curvature. Parallel lines never meet, and geometry follows the familiar rules we learn in school. This kind of universe can be infinite in extent or extremely large but unbounded. It expands forever, but at an ever-slowing rate if matter dominates, or accelerating if dark energy dominates. An open universe, shaped like a saddle. It has negative curvature, meaning space bends outward. Parallel lines eventually diverge, and the geometry is hyperbolic. Such a universe would expand forever, faster and faster, becoming colder and emptier with time. Each of these shapes represents a different destiny for the cosmos, and for everything in it. The critical density. So how do we know which one we live in? The answer lies in something called critical density, the delicate balance point between the pull of gravity and the expansion of the universe. Right after the Big Bang, the universe began expanding. If there had been slightly more matter and energy, gravity would have eventually pulled everything back together, leading to a closed universe that might one day collapse in a big crunch. If there had been slightly less, expansion would have continued forever, an open universe. But there's a razor-thin middle ground. If the density of the universe equals the critical density exactly, expansion and gravity balance perfectly. That produces a flat universe, one that expands forever but never curves back or tears apart. To measure this, cosmologists study how galaxies are distributed, how light bends through space, and how ancient radiation left by the Big Bang, the cosmic microwave background, or CMB, is patterned across the sky. The evidence from the cosmic microwave background. The CMB is our oldest photograph of the universe, a faint afterglow from 380,000 years after the Big Bang. It's the light emitted when the first atoms formed and the universe became transparent. That light has been traveling through space for over 13.8 billion years, carrying with it an imprint of the universe's geometry at that time. By measuring the tiny variations, temperature fluctuations, in the CMB, scientists can determine how space is curved. If space were curved like a sphere, those fluctuations would appear larger. If it were curved like a saddle, they'd appear smaller. In 2003, NASA's WMAP, Wilkinson Microwave Anisotropy Probe, provided one of the most precise measurements ever made. Its results were stunning. The universe appears remarkably flat, within a margin of less than 0.4%. Later, the European Planck satellite, launched in 2009, confirmed this with even greater accuracy. According to Planck's data, the curvature of the universe is so close to zero that if it is curved at all, the radius of curvature is far larger than the observable universe itself. In simple terms, to the best of our measurements, the universe is flat, but it might only appear that way within the limits of what we can see. The observable universe versus the whole universe. Here's where things get even more interesting. When we talk about the universe, we often mean the observable universe, the region we can see, limited by the age of light. Because light travels at a finite speed, and the universe is only 13.8 billion years old, we can only see so far, about 93 billion light-years across when you include the effects of expansion. But beyond that horizon, space continues. We don't know how far it goes. It might extend infinitely. Or it might loop back on itself in ways we can't detect because the scale is simply too vast. If the universe is curved, the curvature radius could be so large that it looks flat to us, the same way Earth's surface looks flat to someone standing on it, even though it's a sphere. So, even a flat universe might secretly be curved, only so gently that we can't yet tell. Topology, the hidden geometry of space. The universe's shape isn't just about curvature, it's also about topology, the way space is connected. Even a flat universe can be finite if it's connected in clever ways. Imagine a video game world where leaving one edge of the screen brings you back from the opposite side, a wraparound universe. This is called a toroidal universe, or a 3D analog of a donut shape. In such a universe, you could travel in a straight line forever and eventually return to your starting point, not because space curves, but because it connects back on itself. Mathematically, it's possible for space to have multiple such connections, forming intricate patterns where the universe folds in higher dimensions. Some scientists have even searched for repeating patterns in the CMB, circles in the sky that could indicate we are seeing the same region of space in multiple directions due to such a wraparound topology. So far, no conclusive evidence has been found, but the possibility remains open. We may live in a universe that's finite, connected, and yet appears infinite. The shape and the fate. The shape of the universe is deeply connected to its fate. For much of the 20th century, scientists thought they knew the answer. If the universe were closed, gravity would eventually win. After billions of years, expansion would slow, stop, and reverse. Galaxies would begin to fall back toward each other. Stars would ignite one last time as everything collapsed into a final, blinding implosion, the Big Crunch. If the universe were open, expansion would continue forever. Galaxies would drift apart, stars would burn out, and the cosmos would fade into a cold, dark heat death, an eternity of emptiness. And if the universe were exactly flat, it would expand forever, but more slowly over time, approaching stillness only after infinite years. But in the late 1990s, astronomers discovered something that changed everything. The universe's expansion is accelerating. The discovery of dark energy. In 1998, two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, measured distant exploding stars called Type Ia supernovae. These supernovae serve as standard candles, objects of known brightness that can be used to measure cosmic distances. To their surprise, they found that distant galaxies were moving away faster than expected. Something, an unknown force, was pushing the universe apart. This mysterious energy became known as dark energy. Dark energy acts like a repulsive form of gravity, driving space itself to expand faster over time. It makes up about 68% of the universe's total energy content, dwarfing both dark matter and ordinary matter. This discovery transformed cosmology. It meant that the universe's fate was not tied simply to its shape, but to the balance between matter, dark matter, and dark energy. Even a closed universe could expand forever if dark energy dominates. The geometry of expansion. To visualize this, cosmologists use a concept called the scale factor, which describes how distances in the universe grow with time. Different equations predict different futures. In a matter-dominated closed universe, the scale factor rises, peaks, and then falls, a cosmic heartbeat that ends in collapse. In a flat universe with dark energy, the scale factor grows exponentially, expansion accelerating forever. In an open universe, it grows faster and faster, approaching infinite separation between all things. The discovery of dark energy suggests our universe is flat and accelerating. This means galaxies far enough away will eventually disappear beyond our horizon, their light stretched to invisibility by the expansion of space. In the unimaginably distant future, only the nearest galaxies, perhaps just our own local group, will remain visible. Could the shape change over time? It might sound strange, but the shape of the universe could evolve. As space expands and the density of matter drops, the effects of curvature can shift. In the early universe, matter and radiation dominated. Now, dark energy does. If dark energy strength ever changes, if it grows stronger or weaker, it could alter the universe's geometry over time. Some theories suggest dark energy might one day reverse, causing expansion to slow, stop, or even contract again, leading to a big crunch. Others imagine the opposite, dark energy intensifying endlessly, tearing galaxies, stars, and even atoms apart in a final big rip. In both cases, geometry, the shape of space itself, dictates the ultimate fate of everything. Measuring flatness with precision. Modern cosmology continues to refine our measurement of curvature. The Planck mission, combined with data from galaxy surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Spectroscopic Instrument, DESI, allows cosmologists to test curvature at extraordinary precision. Right now, the best estimate is that the curvature parameter, denoted as, is within plus or minus 0.001, meaning the universe's deviation from perfect flatness is smaller than 1 part in 1,000. If the universe is curved, its radius of curvature would exceed 250 times the observable universe, effectively undetectable with today's instruments. That's like standing on Earth and trying to see the curve of a planet the size of a galaxy cluster. A universe with no center, no edge. One of the hardest ideas to accept is that the universe has no center and no edge. Wherever you are, it looks the same in every direction. That's the essence of the cosmological principle. The universe is homogeneous and isotropic on large scales. People often imagine the Big Bang as an explosion from a central point into empty space. But that's a misconception. The Big Bang happened everywhere at once. Space itself expanded. Every point in the universe is moving away from every other point, not because it's flying through space, but because space itself is stretching. So if you ask, where is the edge of the universe? The answer is, there isn't one. If you ask, where did it all begin? The answer is, everywhere. The universe may be finite or infinite, curved or flat, but it's centerless, edgeless, and self-contained. The universe as a four-dimensional shape. To go even deeper, imagine the universe as a four-dimensional object. Just as the surface of a balloon is a two-dimensional curved space embedded in three dimensions, our three-dimensional universe could be the surface of a higher dimensional shape expanding in time. In this analogy, galaxies aren't moving through space. They're carried outward as the balloon expands. There's no center inside the balloon. The expansion happens everywhere on the surface equally. If the universe is closed, it could be like a four-dimensional hypersphere expanding in an unseen dimension. If it's open or flat, it might stretch infinitely, like a plane that never ends or a saddle that curves outward forever. We can't visualize this perfectly, but mathematics lets us describe it with stunning precision. Einstein's equations of general relativity, Friedmann's cosmological models, and the modern CDM, lambda cold dark matter, model together describe this evolution, and so far, every observation fits remarkably well. Philosophical reflections on shape. The question of shape isn't just scientific, it's deeply philosophical. If the universe is infinite, does that mean everything that can happen will happen, somewhere? If it's finite and loops back on itself, could light from distant galaxies be circling around and returning to us from the other side, showing us echoes of our own past? And if there's no center, no edge, and no boundary, what does that mean for our sense of place? It reminds us how deeply we are part of the universe, not separate from it, but woven into its geometry, like threads in a cosmic fabric. The atoms in your body curve space, just as galaxies do. You are part of the shape of the universe itself. Summary: the shape we know, and the mystery beyond. Today, the best evidence tells us the universe is spatially flat to an extraordinary degree. It is dominated by dark energy, which drives accelerated expansion. It has no center, no edge, and may be either infinite or so large that it appears infinite. The geometry and fate of the universe are intertwined. One determines the other. But beyond our horizon, the story might be different. Perhaps space curves there. Perhaps the shape changes beyond what light can reach. We may never know for certain. And maybe that's the beauty of it, that even in an age of satellites and equations, the universe still holds mysteries vast enough to humble the human mind. The fate of the universe, heat death, big rip, or eternal rebirth. Everything that begins must one day end. Galaxies, stars, planets, even the atoms that make us, are temporary patterns in a universe that itself is changing. And so, the ultimate question arises: how will the universe end? The present universe, a snapshot in cosmic time. Right now, we live in what cosmologists call the stelliferous era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited, and it will continue for trillions of years to come. Our universe is 13.8 billion years old, a young adult in cosmic terms. Galaxies shine, stars burn hydrogen into helium, and planets like ours orbit in stable systems. It feels eternal to us, but cosmically speaking, it's just a moment. The forces that govern the universe, gravity, nuclear fusion, and entropy are already shaping its destiny. To understand where everything is heading, we must follow the story forward across unimaginable timescales. The next 100 billion years, the end of light. In the next tens of billions of years, the universe's expansion will continue to accelerate, driven by dark energy. Galaxies that are not gravitationally bound to ours will drift away faster and faster. Right now, we can see about 2 trillion galaxies in the observable universe. But over the next 100 billion years, nearly all of them will fade from view. The light from distant galaxies will be stretched by the expansion of space, redshifted beyond detectability. Eventually, only our local group, the Milky Way, Andromeda, and a few small companions will remain visible. They will merge into a single giant elliptical galaxy sometimes called Milkdromeda. The night sky will grow emptier and darker. Future astronomers, if any exist, will see a lonely cosmos, a single island of stars floating in eternal darkness. They may never know there were once billions of galaxies. The evidence of cosmic expansion itself will vanish, hidden by the acceleration of space. The death of stars, when the lights go out. Stars are engines of the universe. They fuse hydrogen into helium, helium into heavier elements, and spread those elements into space through stellar winds and supernovae. But their fuel is finite. The fate of small stars. Red dwarfs, the most common stars, burn their hydrogen slowly and can live for trillions of years. The smallest of them, with a fraction of the Sun's mass, may live for up to 10 trillion years before fading into cold, dim embers called black dwarfs. The fate of Sun-like stars. Our Sun has about 5 billion years of fuel left. When it runs out of hydrogen, it will expand into a red giant, engulfing Mercury and Venus, and possibly Earth. Then it will shed its outer layers, forming a glowing shell called a planetary nebula. The remaining core will cool into a white dwarf, a dense object about the size of Earth but with the mass of the Sun. White dwarfs shine faintly from leftover heat, slowly cooling over billions of years until they, too, fade into black dwarfs, dead stars in an ever-darkening cosmos. The fate of massive stars. The largest stars live fast and die young. They burn their fuel in a few million years, ending in spectacular supernova explosions. These explosions forge heavy elements like gold and uranium, scattering them into space, the raw material for future worlds. Their cores collapse into neutron stars or black holes, depending on mass. And those black holes will become the dominant cosmic structures in the distant future. The degenerate era, the age of black dwarfs and black holes. After roughly 100 trillion years, star formation will cease. There will be no new stars, no new light. The universe will enter the degenerate era, named for the degenerate matter found in white dwarfs and neutron stars. A universe of corpses. The galaxies will now be filled with stellar remnants. White dwarfs slowly cooling into black dwarfs. Neutron stars, the frozen hearts of once great suns. Black holes lurking silently in the dark. The universe will be a graveyard of what once was, cold, silent, and vast beyond imagination. Occasionally, through gravitational interactions, these remnants will collide. Two black dwarfs may merge, briefly reigniting nuclear fusion for the last time in the universe. But these moments will be rare, cosmic flickers in an endless night. Galactic dissolution. Even gravity will struggle to hold galaxies together. Over tens of trillions of years, close encounters between stars and remnants will gradually fling them out of their galaxies. Eventually, the galaxies themselves will dissolve, their remains scattered across expanding space. The cosmos will become a thin mist of degenerate matter, white dwarfs, neutron stars, and black holes, drifting farther apart forever. The black hole era, the reign of darkness. The next great epoch belongs to black holes. They are the ultimate survivors of the universe. Over the next 10 to the power of 40 years, that's 10 followed by 40 zeros, black holes will dominate cosmic structure. Every large galaxy will contain a supermassive black hole at its center, millions or billions of times the mass of the Sun. Even as everything else fades, black holes remain, swallowing matter, merging with each other, shaping the dark geometry of space-time. Hawking radiation. But black holes, too, are not eternal. In the 1970s, Stephen Hawking discovered that quantum effects near the event horizon cause black holes to emit tiny amounts of energy, Hawking radiation. Over unimaginable timescales, this radiation will cause black holes to evaporate. Smaller black holes will vanish first. Supermassive black holes, like the one in our galaxy's core, will take 10 to the power of 100 years to evaporate, a number so vast that it exceeds comprehension. When the last black hole finally evaporates, it will release one final flash of energy, a whisper of light before the cosmic silence. The dark era, the end of matter. After the last black hole fades, the universe will enter its final known stage, the dark era. By this time, the temperature of space will have dropped near absolute zero. No stars, no light, no heat, only cold radiation and decaying particles drifting in infinite darkness. But even this is not the absolute end. There are deeper layers still. Proton decay, if it happens. Some theories of particle physics, particularly grand unified theories, GUTS, predict that protons, the building blocks of atoms, may not last forever. If protons decay, it would take about 10 to the power of 34 to 10 to the power of 40 years for half of them to vanish. That means all ordinary matter, all atoms, all elements, all physical structure, would eventually dissolve into a thin soup of electrons, positrons, neutrinos, and photons. Even the cold remains of black dwarfs and neutron stars would crumble into radiation. However, proton decay has never been observed. If protons are truly stable, matter could persist indefinitely, but it would still be useless, frozen, and scattered across a lightless void. Entropy and the heat death. No matter how long it takes, entropy, the measure of disorder, always increases. Energy spreads out. Differences fade away. The universe moves toward equilibrium. In the end, all usable energy will be gone. No process, no star, no machine, no thought will be possible. The cosmos will reach maximum entropy, the so-called heat death. It won't be hot, but cold, a uniform sea of particles at the lowest possible energy state. No structure, no change, no time as we understand it. Just stillness. Beyond the end, theories of cosmic rebirth. But is that truly the end? Perhaps not. The universe may have surprises left even after eternity. 1. The Big Crunch. If dark energy ever changes sign, becoming attractive instead of repulsive, expansion could slow, stop, and reverse. Galaxies would draw together, heat would return, and the universe would collapse back into a single point. That point could mark the end of one universe, or the beginning of another. In this cyclic model, the Big Bang and Big Crunch are two sides of the same eternal rhythm. 2. The Big Bounce. A related idea is the Big Bounce, that our universe is just one phase in an infinite cycle of expansion and contraction. Each time the universe collapses, quantum effects trigger a rebound, a new Big Bang, birthing a new cosmos. In this view, time has no beginning or end, only endless renewal. 3. Quantum rebirth. At the smaller scales, space-time itself may be quantized, made of discrete, vibrating loops as proposed in loop quantum gravity? If so, singularities like the Big Bang and black holes might not be true points of infinity, but transitions to new spacetime regions. A black hole in one universe might become a white hole, the birth of a new universe in another. Thus, our universe could be the child of another, born from the death of a star long forgotten. 4. Vacuum decay. There's another, stranger possibility: vacuum decay. According to quantum field theory, the universe might not be in its most stable state. If our vacuum is metastable, a random quantum fluctuation could trigger a transition to a lower energy vacuum, a new version of the universe with different laws of physics. This would spread outward at nearly the speed of light, destroying everything in its path instantly and silently. But don't worry, the odds of it happening anytime soon are astronomically low. Still, it's a reminder that even in apparent eternity, change can come without warning. The quantum eternity. Even in the heat death, quantum physics may prevent absolute stillness. Particles and fields can fluctuate, even in empty space. Over vast timescales, these fluctuations might occasionally form temporary structures, perhaps even entire new universes. Physicist Alan Guth calls this quantum eternal inflation, the idea that universes continuously bud from the quantum vacuum, forever renewing creation. In such a reality, nothing ever truly ends. Energy and matter dissolve, but existence continues in endless transformation, one cosmos giving rise to another across infinite time. Humanity's place in the timeline. It's humbling to realize where we stand in all this. We live near the beginning, in the first heartbeat of cosmic history. All of human civilization fits within the last billionth of the universe's lifespan. If time were compressed into a single year, the Big Bang would be January 1st, stars forming by February, galaxies by March. The solar system wouldn't appear until early September. Dinosaurs would vanish on December 30th. Humans would appear just seconds before midnight on December 31st. We are newcomers in an ancient, unfolding story, but we are also the first known beings able to tell it. The philosophy of the end. When we think of the universe's end, we often feel fear, the loss of light, of meaning, of time. But perhaps we can see it differently. The universe is not dying. It is transforming. Energy doesn't vanish. It changes form. Matter decays into radiation. Stars give way to dust. Black holes return their energy to space. And perhaps consciousness, the awareness that arose within the universe, is part of that cycle. Maybe our thoughts, our stories, our very act of wondering, are the universe knowing itself before returning to silence. In the end, the cosmos is not just a place. It is a process, eternal, evolving, mysterious beyond imagination. Final reflection. The night sky above you tonight, every star, every point of light, is temporary. But the atoms in your body, forged in long-dead stars, will outlast suns and galaxies. They will drift, scatter, and one day perhaps help seed another universe. In that sense, you are immortal, not as a person, but as a pattern in the great cycle of existence. The universe began in fire and light. It may end in darkness and silence. But even silence is not nothing. It is the pause between cosmic notes, the breath before the next creation. And perhaps, long after we are gone, another being, in another time, will look into their own night sky and wonder, where did it all come from? And the story will begin again. What is nothing? The human mind struggles to picture nothing. When we think of nothing, we imagine darkness, but darkness is still something. It's still a kind of light, just with low energy. But before the Big Bang, even darkness didn't exist. There was no space, no time, no energy, and no place for anything to be. So when we ask, what existed before the universe? The answer might be the question itself doesn't make sense, because time itself, the before and after, hadn't yet begun. To understand this, physicists go back to the smallest possible instant of existence, the Planck time, 10 cubed seconds after the Big Bang. That's 0.000000000000000000000000000000001 seconds. At that time, the universe was smaller than an atom, smaller than a proton, smaller than anything we can truly imagine. This is the frontier where quantum mechanics and general relativity, the two great pillars of physics, both apply, but cannot yet be unified. It's the place where our understanding ends, and the true mystery begins. The Planck era, when physics breaks down. During the Planck era, the entire universe existed as a kind of quantum foam, a storm of energy fluctuations, constantly appearing and disappearing in fractions of a second. The energy density was so high that gravity itself behaved like a quantum field. Space-time wasn't smooth. It was turbulent, constantly warping, twisting, and bubbling like a boiling ocean. At this moment, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were still one single force, perfectly unified. This is the dream of theoretical physicists, the theory of everything, the single equation that could describe all the forces in one elegant framework. Many believe that string theory or loop quantum gravity could hold that answer. In string theory, all particles, electrons, quarks, photons, are not points, but tiny vibrating strings of energy. Each vibration produces a different particle, much like a musical string produces different notes. If true, then the entire universe might be a cosmic symphony, a vast orchestra of vibrating strings, playing the song of creation. The quantum birth, how nothing became something. But how could something emerge from nothing? How could an entire universe appear from the void? The answer may lie in quantum fluctuations. According to quantum mechanics, even in a perfect vacuum, energy can briefly appear and disappear, borrowing energy from nothing, as long as it's returned quickly enough. This is known as Heisenberg's uncertainty principle. In ordinary space, these fluctuations are tiny and harmless. But in the beginning, when space itself was quantum and unstable, one of these fluctuations may have become large enough to inflate, to become everything. It didn't happen in space, it created space. This is the true beginning, the birth of space and time from a quantum fluctuation. And in that instant, the universe began to expand faster than light itself. This was the start of cosmic inflation. The inflationary epoch, the universe expands in a blink. Imagine a speck of energy smaller than an atom. In less than a trillionth of a second, it expands into a region larger than the observable universe. That's inflation, a burst of expansion so fast and so immense that it smooths out the entire cosmos. It's as if the universe took a deep breath and instantly stretched space-time beyond imagination. During inflation, tiny quantum fluctuations were stretched to cosmic size. Those fluctuations became the seeds of galaxies. The universe became flat, uniform, and filled with potential energy. When inflation ended, that energy didn't disappear, it transformed. It became matter and radiation, filling the cosmos with a hot, dense plasma. This is what we now call the Big Bang. So, the Big Bang wasn't the start, it was the aftermath of inflation. The universe didn't explode into space. Space itself expanded, carrying everything within it. The first second, the era of fire. Now, we enter the first true second of the universe, a second that would define everything that followed. At this time, the universe was unimaginably hot, about 10 billion Kelvin. Space was filled with a thick soup of energy. Photons, quarks, electrons, neutrinos, and antimatter. Particles collided so violently that matter and antimatter constantly appeared and annihilated each other. For every billion pairs that destroyed each other, one extra particle of matter survived. That small imbalance, 1 in a billion, is why everything exists today. Without that tiny asymmetry, there would be no atoms, no stars, no planets, no life. The strong force and the birth of protons. Around 10 seconds, a millionth of a second, after the Big Bang, the temperature cooled enough for quarks to combine. The strong nuclear force bound them together into protons and neutrons. The universe now had the basic building blocks of all atomic nuclei. A new chapter began, nuclear synthesis. The first 3 minutes, the cosmic recipe. Between about 1 second and 3 minutes, the universe continued to expand and cool. During this short but critical period, the first atomic nuclei formed. Protons and neutrons fused to create deuterium, heavy hydrogen, helium-3, helium-4, and trace amounts of lithium. This process is called Big Bang nucleosynthesis. By the end of these 3 minutes, about 75% of the mass of the universe was hydrogen and 25% was helium, with a whisper of lithium. Those same elements still make up nearly all visible matter today. The stars that would later form billions of years afterward would use these ingredients to create heavier elements, like carbon, oxygen, and iron, in their fiery cores. The first 380,000 years, the era of light. After the first 3 minutes, the universe was still opaque. Photons, particles of light, could not travel far without being absorbed by charged particles. Space was a foggy, glowing plasma. Only after 380,000 years did the universe cool enough for electrons to join with nuclei, forming neutral atoms. This moment is called recombination. Suddenly, light could travel freely through space for the first time. That ancient light is still traveling today, stretched by the expansion of the universe into microwave radiation. We can still see it as the cosmic microwave background, CMB. It is the oldest light in existence, a faint echo from the dawn of time. The cosmic dark ages. After the release of the CMB, the universe went dark. There were no stars yet, only hydrogen and helium gas drifting through vast darkness. For the next 100 million years, the universe was silent. Gravity worked slowly, pulling matter together, forming the first clouds that would one day collapse into stars. This was the cosmic dark age, a long night before the first dawn. But even in the dark, structure was forming. Tiny irregularities in the density of the gas, born from those original quantum fluctuations, began to grow. These ripples would eventually become the first galaxies, the first stars, the cosmic dawn. Around 100 to 200 million years after the Big Bang, the first stars ignited. They were giants, hundreds of times more massive than our Sun, burning intensely and living briefly. These first stars, called population 3 stars, contained only hydrogen and helium, no heavier elements. When they exploded as supernovae, they created the first carbon, oxygen, and iron, the materials needed for planets and life. From their ashes, new generations of stars were born, richer, more complex, capable of forming solar systems. One of those generations, billions of years later, would give birth to a small yellow star and a pale blue planet orbiting it. The philosophy of creation. The birth of the universe is more than a scientific event. It's a story of transformation. It tells us that even from emptiness, beauty can arise. That chaos can give rise to order, and that from a single spark, an infinite cosmos can unfold. We often ask, why is there something rather than nothing? Science may never fully answer that, but it shows us that nothing is not empty. It is filled with potential, restless, creative, unpredictable. Perhaps creation is not a single event, but a constant process. Every moment, every atom, every breath is part of that same unfolding mystery. The universe awakens. From quantum foam to galaxies, from pure energy to life itself, all of it emerged from the same origin. In the language of physics, we are fluctuations in a field, patterns of energy organized by time. In the language of poetry, we are the universe looking back at itself. When you look at the stars, you are seeing the afterglow of your own beginning. The atoms in your body, hydrogen, carbon, oxygen, were forged in stars, which were themselves made from the ashes of the Big Bang. In a very real sense, you are not in the universe. You are the universe, conscious for a brief moment, dreaming about itself. Final reflection. And as you drift towards sleep tonight, imagine this. 13.8 billion years ago, time itself took its first breath. From that breath came light, matter, gravity, stars, planets, and life. And now, you, a being made of stardust, are thinking about the beginning of it all. The universe is still expanding, still cooling, still unfolding its endless story. And perhaps, in some distant future, when it begins anew, the spark that once became you will return again, as part of another dream, in another sky. Sleep peacefully under the same stars that were born in that first second, because you are part of that beginning, and always will be.